Mandi Thran, who I think most of you are familiar with Mandi. She's at the Water Research Lab at UNSW. So Mandi completed her PhD in 2000, I believe officially in 2000, at the University of Sydney. And so her work at the time was really focusing on hydrodynamics and sediment transport processes on the shelf, including work I believe she's going to be talking about today. Since February of 2020, she's been a postdoctoral research associate at UNSW, working on essentially early warning systems to predict coastal flooding and erosion. So we've had pleasure at UWA to also work closely with Mandi and the group at Water Research Lab on that project. So Mandi is Mandi there?
I am.
You are?
Yep. Can you hear me?
Yep. So
right,
I think
awesome.
You should be able to share your screen, but Mandi's going to be talking about numerical simulations of a long slope, downslope, and cross-shelf flows on passive margins, which should be quite interesting to hear.
All right, thank you so much, Ryan. So let me just get this shared here. All right. All right, can everyone see that okay? Yeah, good. All right. Thank you so much, Ryan, for that introduction. He actually didn't ask me for any information regarding my background, so I really appreciate the work that you did to get that little introduction up. As Ryan has said, my name is Mandi Thran, and I joined the Water Research Lab at UNSW back in February under the supervision of Professor Ian Turner and Dr. Macharlie and Dr. Kristen Splinter. And there I am working on building a prototype early warning system for coastal erosion. And so I wrapped up my PhD at the University of Sydney at the School of Geoscience at the beginning of the last year, and I worked on numerical modeling of hydrodynamic and sedimentary processes on continental margins. And so this talk will reflect a lot of what I did during my PhD. And so when I'm giving these types of seminars, I'm used to speaking to people who've spent a great deal of time studying the deep sea and its sediments. And so it can seem like a niche area of science for those who aren't really acquainted with it. But I'll pose this question to you now. What comes to mind when you think of the deep sea? And maybe you think of these deep sea vintage diving suits, or maybe you think of the deep sea hydrothermal vent systems, or perhaps the discovery of the Titanic comes to mind, or maybe James Cameron's recent expedition to the bottom of the Marianas Trench comes to mind as well, or maybe you think of Finding Nemo. And so on further reflection, I was actually quite surprised at how much the deep sea has really entered our popular discourse. And so it seems that the deep sea has captured our imaginations for centuries, perhaps millennia, since there are ocean deities that are actually represented in Aboriginal Dreamtime stories. And perhaps because it's so inaccessible and such a remote and mysterious part of the world, that this domain has remained very fertile ground for the human imagination. And today it's very fertile ground for scientists who want to make new discoveries and create new knowledge. But although people have been going on ships and they've been exploring the oceans for centuries, it took quite a long time for modern deep sea research to really spin up as we know it today. And so for the most part, prior to about 1870, scientists thought that the deep sea was a fairly uneventful and cold and dead place. But then explorers, they began to pick up some interesting stuff, and submarine telegraph cables started randomly breaking without a clear explanation as to why. And the echo sounder, which uses sonar technology, was invented and refined during World War II, and this allowed countries to efficiently map the seafloor and to more effectively fight each other with submarines. And this culminated into the first comprehensive maps of the seafloor. And this revealed that the seafloor was not a boring and flat and dead place. It has stunning topography. And so there's a lot more going on down here than what was originally thought by the early modern scientific community. And so this brings me to my seminar today. And so just to give you an idea of the scope of this talk, I'm going to mimic the overall structure of my PhD thesis, and this focused on studying hydrodynamic and sedimentary processes on the edges of the continents where the shallow meets the deep sea. And so I'm firstly going to provide with a bit of background on why passive margins such as the Great Barrier Reef margin here are not only interesting, but are worth knowing about for a lot of practical reasons too. And next, I'll go into the substance of my thesis, and I'll tell you 3 short stories about how we numerically simulated along slope flows, down shelf and downslope flows, and cross shelf flows. And I'll talk about some of the implications of these findings as well. And then finally, I'm going to give you my perspective on where I think the frontier of numerical modeling is. And while I don't expect anyone here to really cite any of the Continental margin research papers that I've come out with recently, I think there is room for contemplating the role of numerical modeling of Earth systems more generally. And this is as we continue to think about how to push this field forward and how to innovate within this discipline. Okay, so just to generally show you where we are, passive continental margins, they're shown here in blue, and they're located anywhere where there isn't a lot of earthquakes. In other words, they're not located along active plate boundaries. And you can see the classic Pacific Ring of Fire situated here in red. And they sit fairly quietly on the outer edges of continents that have been broken up by plate tectonics for a long time. And here's a generalized schematic of a continental margin here showing some of the common features that I'll be talking about today. And so we have the coastline, which you guys are most familiar with here on the landward edge of the margin. And then the continental shelf extends out to about 100 meters water depth, and then it plunges very quickly down to about a few kilometers depth. And this drop off is called the continental slope. And then this is rimmed by the continental rise and the abyssal plain. And as I mentioned before, this area of the world, the deep sea, is a place of enormous scientific intrigue, but scientific intrigue alone is not enough to pay the bills. So I will offer some practical reasons for why you should care about what's happening on submerged passive continental margins. And the first is the role that deep sea sediments play in offering very rich proxy records that help scientists to reconstruct Earth's past ocean and climatic changes. And in order to contextualize our current anthropogenic change, we have to have an understanding of how much and how often and by what mechanisms the Earth's oceans and climate have changed in the past. And so deep sea sediments, they are critical proxy records for understanding these kinds of changes. And so it's not all that uncommon to see studies on deep sea sediments in IPCC reports. And the second reason for studying passive margins is to know about some of the geohazards that originate there. And so there's a lot of infrastructure on the seafloor that we rely on. And I mentioned submarine cable breaks before. And there's this common misconception that the majority of our communications is facilitated by satellites. But according to the UNEP, about 95% of this traffic is actually routed through fiber optic cables that traverse the seafloor. And so the famous cable break that I mentioned earlier was actually caused by a submarine landslide. And this also very famously triggered a tsunami that devastated Newfoundland. And oil rigs have also been damaged by submarine landslides during storms. And so all of these hazards have occurred on passive margins. And the last key reason is the fact that passive margins form the dominant tectonic setting for hosting the world's hydrocarbon reservoirs, and they contain about 35% of the world's giant oil and gas fields. And so in order to better target these kinds of resources, you need to understand something about the hydrodynamic and sedimentary conditions that would have favored their formation. There is a fourth reason, which I hinted at earlier, and a lot of early modern deep sea exploration was in fact motivated by the need to detect enemy submarines during wartime and to avoid crashing your own submarine into an undersea mountain. And if you're wondering if this has ever happened before, it absolutely has. So using numerical models to study deep sea hydrodynamic and sedimentary processes is relatively new. And a lot of observational and hard rock geologists tend to view this discipline with a bit of skepticism, and they endearingly refer to us as Nintendo geologists. So what role does numerical modeling play in these geological studies of the deep sea? Well, firstly, numerical models are used to test hypotheses about process in a way that is consistent with physical laws, or in a way that is consistent with the empirical representations of these physical laws. And they're very handy if you're trying to understand processes that may be operating in a very remote and inhospitable and inaccessible place, such as the deep sea. So in this way, they can act as an independent line of evidence to support or establish whether or not a process is actually taking place. And secondly, once those processes are sufficiently captured by the model can be used to make predictions. And in this branch of geology, we're not so concerned about making predictions about the future, but about areas that are undersampled, areas of the seafloor that are undersampled and are awaiting direct validation, for example, or about lesser known time periods in Earth's history. And so in this way, numerical models and simulations, they can help offer us a much more realistic idea of what's happening on the seafloor than what our imaginations alone can offer. And so continental margin research is truly a very rich area of marine geology, and I'm really only giving you a very small glimpse into this very expansive scientific subdiscipline. But here we are again. We have a schematic of a generic passive continental margin. And my first short story is going to focus on what I call along slope flows. And these are currents that travel parallel to the continental slope. And here I'm going to focus on deep sea currents called contour currents because they follow bathymetric contours. And so the story is centered around the second chapter of my thesis, which was published as a paper in Earth and Planetary Science Letters. And it focuses on the deep sea sedimentary signatures of along slope flows, which are called Contourite drifts or Contourites. And so I'll start off by defining what a contourite is for you. So you can think of a contourite drift as a pile of sediment that has been pushed around by a contour current when the current winds around an obstacle on the seafloor. And the way that they develop is somewhat analogous to the way that a snowdrift will develop under high winds. And so this here is a time lapse of a snowdrift piling up during a blizzard. And you can see that the overall structure of the snowdrift is quite reminiscent to that of a contourite, and it's imaged here. The subsurface of the contourite is imaged here in what's known as a seismic reflection profile. And so you have an obstacle on the seafloor, which in this case is the continental slope, this moat-like feature which sits right next to the obstacle, and then the drift with its piled on sediments right next to the moat feature. And so paleoceanographers and paleoclimatologists, they really like contourite drifts because they pile up next to seafloor features relatively quickly on geological timescales. And because deep sea sediments, again, they often contain very rich proxy records, contourites can help yield high resolution reconstructions of paleoceanographic and paleoclimatic change. And so just to recap some basic oceanography here, paleoceanographers and sedimentologists, they figured out that the contourites seem to be found along the trajectory of what is known as the global ocean conveyor belt, which refers to the global configuration of the Earth's major currents. And sometimes it's referred to as thermohaline circulation as well. And so there seemed to be some overlap between where the contourites were and where the trajectories of these currents were, but the precise mechanisms that are responsible for forming contourites aren't exactly known still. And so there are all kinds of people who are interested in understanding where these contourites are distributed on the seafloor because they want to actually target them in drilling campaigns. But in order to more effectively target them, we have to have an understanding of the conditions that favor their formation. And so because ocean dynamics are notoriously difficult to observe, as many of you know, we turn to an ocean circulation model called the modular ocean model. And here is an animation of the output here. I'll zoom head towards an interesting bit here. And so armed with this ocean model, We started out with a very broad objective, and we just wanted to see if areas that exhibited strong bottom current activity along the global ocean conveyor belt overlapped with areas that had contourites in them. And so this hypothesis has actually been accepted for a while amongst the community of people who study them, but it hasn't really been tested in this way before using a global ocean sea ice model. But before we could do anything, we had to build and digitize our database. And so these are all the features that we revisited. We went through the literature. It was a painstaking process of going to the original papers and georeferencing all the figures and very carefully refining the coverage of each of these individual features. And I'll note that before I started this work, I actually didn't need glasses, but now my eyes are just ornamental without them. And so this here is a flyover view of all of the features that we looked at. And so just looking at the results now, this is a global outlook of the newly refined Contourite coverage. And the features are all actually labeled here and they're shown in orange. And this underlying raster here is the mean annual computed bottom current speed. And so the red areas are indicating areas where the currents are moving very quickly in shallow areas. And the blue areas are indicating high current speeds in some of the deeper areas of the ocean basin. And so looking at this here, strong bottom current activity and Contourites, they do appear to overlap. And we do indeed find lots of features along this simulated global ocean conveyor belts. So a good example of this is in the northern North Atlantic, where deep water formation occurs. There are lots of Contourites here that are very well studied. You tend to get them along the western sides of ocean basins as well. These are where strong western boundary currents are, and you get them at ocean gateways too. And so this confirms what many others have thought about what controls Contourite distribution, at least on a global first order level. But something strange happens when we start to quantitatively assess how fast the currents are actually moving in these areas. And so just to explain what this is a violin plot, and this represents all of the points in our model on the seafloor that were classified as either having Contourites on them or just the rest of the ocean in general. And so the fatter the violin is, the more points that are clustered around a particular value of the y-axis. And this is simulated mean annual bottom current speed. That's right here. And so when we actually went and extracted the bottom current speeds, we noticed that on average, areas that had Contourites in them didn't actually experience speeds that were that much faster than in the rest of the ocean. And this is an issue because Contourites, allegedly, they need faster currents in order to be able to form them and to push the sediments around. And so we found that bottom currents on average move less than about 4 centimeters per second everywhere. And so this is a problem. Because the commonly accepted thresholds for moving silt-sized grains around ranges from about 10 to 15 centimeters per second. And this is based on what I've read from lab and field studies. And in Contourites, you don't find anything smaller than silt. So I'd conclude here that the mean values we extracted from the model really aren't fast enough, and aren't anywhere near fast enough to laterally redistribute, resuspend sediments and move them around. And this is essential for actually building Contourites. And so in light of this result, we decided to look at the maximum and standard deviation values. And this is where the Contourite areas really start to differentiate from the rest of the ocean. And so over Contourites, the bottom currents achieve much higher maximum speeds than the rest of the ocean, and they tend to achieve these 10 to 15 centimeter per second thresholds that I was referring to before. And the standard deviations, they tell a similar story where the bottom currents are fluctuating in intensity much more over Contourites. And so in this field, it's often assumed that a bottom current has to kind of be quasi-stable and persistent enough to continuously rework and move sediments around and build the drift. But I would actually argue here that it's more important for a bottom current to be fluctuating in intensity on intra-annual scales, because this allows sediments to be reworked, but it allows sediments to accumulate during more quiet periods. And so with this in mind, our first result that we got actually does make a lot of sense, because if the currents are moving too quickly all the time, they're just going to erode the Contourites away, and they're going to create hiatuses in the geological record. And so are these results consistent with what we find in the field? It turns out field measurements echo the model pretty nicely. And so some researchers in America have found that the deep western boundary current moves towards the equator about 2 to 4 centimeters per second on average. And this is similar to what the model is suggesting as well. And again, this is too slow, I assert, to rework sediments year round. But then if you look at a time series of bottom current speed in this area taken from current meters, you notice these episodic events in bottom current speeds over the course of the year, and the maximum speeds are quite similar to what the model is actually producing. And so these episodic events, they also coincide with instances of light scattering, and this light scattering indicates that there are sediments in the water column and they're being moved around. And so what does this all mean when we then dive into the deep sea sediment record to make an interpretation? I would argue here that the sediments themselves in the Contourite don't necessarily reflect persistent everyday background flow conditions. They would more readily preserve these episodic high energy current events, and these energetic states only occur during a fraction of the year. And so this carries significant implications for reconstructions of the global ocean conveyor belts, because we must be aware of this potential bias in the sediment record, or else you might conclude that the global ocean conveyor belts, or bottom currents in general, were moving faster than they actually were. And so if you decide to accept my hypothesis that bottom current fluctuations are more important for building drifts, then this provokes the question, what actually is causing these fluctuations? And it turns out that just like the atmosphere experiences cyclonic storms, the ocean kind of experiences cyclonic storms of its own. And sedimentologists refer to these as benthic storms. And this is when lots of sediment gets kicked up on the seafloor. You were actually seeing those benthic storm events in the light scattering data that I showed in a previous slide. And so this is a plot showing mean annual bottom eddy kinetic energy, which is computed in our model. And we found that eddy kinetic energy was 3 times higher in areas with Contourites than in the rest of the ocean. And so the cool thing about this finding is that there's a team in the US who came up with this hypothesis, a similar hypothesis, completely independently from us, and they studied benthic storms using field measurements. And so they also think that ocean eddies are responsible for periodically pushing sediment around in the deep sea and causing benthic storms. And we think that Contourites are the long-term geological consequence of these repeated benthic storm events. And so we have a situation where the geological data, the observations, and the measurements and the models appear to be converging on a common mechanism, which from an interdisciplinary perspective is ideal. Okay, so just going over some of my conclusions for part 1. We found that the modeled mean annual bottom current speeds weren't fast enough to continuously resuspend and redistribute sediments throughout the year. And this is consistent with what's been reported in the field as well. And we instead found that these high speed intra-annual episodic current events may be more important for building Contourite drifts. And then we therefore suggest that the deep sea sedimentary record should be interpreted bearing in mind that there is this potential bias in the record where Contourites could be biased towards preserving these higher energy events rather than ambient everyday background flow conditions. Okay, on to my next short story now, where I'm going to talk about modeling what I call downshelf and downslope flows. And in the context of my thesis, these include low stand rivers, or rivers that flow onto the continental shelf during times of lower sea level, and turbidity currents, or high density currents that are filled with sediments and they cascade down the continental slope. And so for this story, we're going to go to the Great Barrier Reef, and I'm going to discuss a highlight of the study. And it illustrates how the Great Barrier Reef helps to shape some of the canyons that we find on the continental slope. And so I think we all know and love the iconic Great Barrier Reef, and hopefully you've been lucky enough to go diving there and see all the spectacular wildlife. And you may have heard it be referred to as the world's largest structure, single structure made by living organisms. And these people aren't wrong, because beneath all the pretty stuff that you find at the surface, there are these massive carbonate platforms that sit right on top of the continental shelf, and they're made up of previous generations of the Great Barrier Reef that have been built as sea level has fluctuated over time. And the reefs are not the only interesting thing that can be found on this margin. So if you go a little bit deeper, you find a fantastic system of canyons on the continental slope. And so here we're looking horizontally into the continental slope, and you can see the shelf edge in the bathymetric relief as well, and some of the carbonate platforms that you can find in pink here. And so marine geologists have known about these canyons for a while, but not a lot is known. There's not really a consensus on how they are formed. And so basically there are two schools of thought about how submarine canyons in general are formed. And the first hypothesis states that submarine canyons are constructed through this bottom-up mechanism where you have initial failing of the slope towards the bottom, and this creates geomechanical instability within this developing canyon. And then the failures continue retrogressively up the slope until the canyon head finally breaches the shelf edge here. And the second hypothesis argues for a more top-down approach where these canyons are cut by this process called turbidity currents or turbidity current action. And so turbidity currents are hyperpycnal currents that are filled with sediments, again, over-concentrated with sediments, and this causes them to fall very quickly down the continental slope. And so you can actually see a turbidity current being modeled in a lab here. And so there's one problem with this second hypothesis in our area, though, because canyons, submarine canyons, are often continuations of onshore rivers because the rivers can provide the sediments that help to trigger these turbidity currents. But on the Great Barrier Reef margin, there's a giant reef in the way. And so even during times of lower sea level, you have reefs that are potentially blocking the rivers from reaching many parts of the continental slope. So this has compelled geologists to resort to this kind of first hypothesis about how they form. And so in terms of our modeling strategy, we set out to do something completely different, and it didn't end up working. But while we were doing these runs, we took a bit of a shotgun approach when it came to these geomorphological features, and these features included the canyons. And we basically just tried to reproduce as much as we possibly could with this model. And so just to show you where we are, we're on the central part of the northeastern margin of Australia here. And here's Cairns, and the coastline's in green. The shelf is in light blue, and the platforms, you can see they're in lighter blue here. And you can hopefully see some of the canyons as well in this digital elevation model. And so we're modeling this entire margin with a code called Badlands, and I'm not going to go into all the details of the code here, but this is a schematic of everything that it attempts to simulate. And so rivers transport sediments, and this is modeled using an empirical stream power formulation. And then once those sediments hit the ocean, the sediments are reworked by waves and longshore currents. And they can also be deposited downslope by turbidity currents. And so this is an example of some of the model output looking into the continental slope again now. And we're starting from the last ice age. Sea level was about 120 meters lower than it was today. And you can see how the shoreline changes as sea level rises and inundates the shelf and causes the reefs to start growing here in orange. And to our surprise, the canyons actually appeared in our model in the first round of testing. And so here in the below panel, the blue denotes eroded areas and the red indicates areas where sediments are being deposited. And so the canyons are incising quite clearly in the model, and they're emulating the morphologies that we actually see in the bathymetry above. And part of what we wanted to do also included removing the reef structure to see what impact the reef structure had on the development of these features. And so watch what happens when we ran an identical simulation, but the reef structure was removed. And so we get, instead of canyon incision, we get this net deposition on the slope. And we thought this was very odd because we knew that the carbonate platforms in the previous simulation, they were blocking and rerouting low stand rivers, and they were preventing them from actually accessing these parts of the slope here. So the mechanism for incision wasn't obvious at first, but then we realized that the carbonate platforms were actually providing a lot of steep topography and positive relief. And so this causes sediments to erode more quickly on the outer shelf, and then causes these turbidity currents to be triggered in the model. And this seismic profile was taken from the study area, and it also contains something quite interesting. And so these little dips that you see right here, these are actually intersections or cross sections of the canyons here and some of the rills and gullies that make up the canyons. And the authors interpret that these canyons would have been actively incising from at least the last 80,000 years or so. But when you go back in the geological record to sequence maybe 6 or so, right around the time where the Great Barrier Reef started to form, they start to interpret these broad paleo valleys instead of these narrow rills and gullies. And so this suggests, and they've suggested that the canyons are actually quite young, possibly younger than the Great Barrier Reef itself. And so our modeling suggests, and this suggests, that the formation of the canyons may actually be conditioned by the reef structure being there. And so here's a schematic that just summarizes some of the key processes that we modeled. So when the reef structure is exposed here, we found that the reef structure actually reroutes onshore rivers before they reach the shoreline. And additionally, the reef structure provides that steep topography and also provides the sediments needed in order to trigger turbidity currents in the model. And these turbidity currents help form the canyons through a more top-down mechanism. And if you'd like to read more about that work, you can find a blog post about it here. You can read it instead of reading the paper. Okay, on to the third short story now, where I'm going to talk about cross-shell flows. And this will probably be more relevant to this audience than anything else I'm going to talk about today. And I'll be talking about tsunami propagation. And so for the third project, I used modeling to explore whether the Great Barrier Reef could offer protection against tsunamis. And it's currently, and this article is currently in press for natural hazards, and I anticipate it will be out in the next couple weeks or so. And so we'll be focused on the same area of the Great Barrier Reef as before. And just to give you a bit of context, back in 2008, when all of this multi-beam was collected, there were some very large submarine landslides that were discovered on the Queensland Continental slope. And we knew from previous events that submarine landslides can actually trigger tsunamis. And the most notable modern event was the 1998 Papua New Guinea event. And an underwater landslide triggered a tsunami with run-ups of up to 16 meters. And so after looking at the bathymetric data, documenting what was there, a colleague of ours discovered a precarious looking block on the upper slope here. And this is surrounded by other landslide scars and debris here. So we initially were very interested in figuring out how big of a tsunami this could potentially trigger if it were to fail. And so we came up with a plan to try and simulate it. But as we were coming up with this plan, we recognized, of course, that this isn't an ordinary continental shelf. It's dominated by the Great Barrier Reef, and coral reef environments are very structurally complex. And this has consequences for wave propagation. And as many of you very well know, in cases of wind waves, it's been very well demonstrated that they undergo significant energy loss and attenuation in areas with coral reefs because of increased bottom friction that they inflict due to their roughness. And there's another factor that adds complexity to this area. And I've already discussed this, this structure that underlies the modern Great Barrier Reef here. These carbonate platforms that form the reef structure can be very tall, and this makes them quite formidable obstacles to passing waves. And so here we have this ecosystem scale complexity to keep in mind, in addition to the bathymetric scale complexity that is introduced by the reef structure. And so the aims of the third project were as follows. Number one, we wanted to determine how large of a tsunami the Noggin block could produce if it were to fail under present day sea level conditions. And we actually went on to model an additional bigger slide that was described in the bathymetry. But because this is such a unique area, we also became more interested in tsunami propagation more generally. And we eventually decided to simulate a hypothetical Solomon Islands earthquake case too. And we wanted to test the impact of coral cover on tsunami and wave energy loss and the impact of the coral reef platforms themselves on tsunami propagation. And so I don't have time to go into all of the modeling methods here, but I'll just introduce how we handled the reefs, which I think is the key part of this study. And so on the shelf, we set up some scenarios to isolate the impact of the reef. And so for our first scenario, we took the coral platforms, or the carbonate platforms here, and we made them rough. We put coral cover on top of them. And so this is the bottom shear stress formulation used in the model. It's a very common one in these kinds of models. And if you want to increase the roughness of the seafloor, then you play around with this parameter CD here. And we chose this value because it was empirically determined from a reef platform that lies just out of view of this map here. So we really wanted to try to pick a value that was actually representative of the roughness of the Great Barrier Reef in our study area specifically. For our next scenario, we then removed coral cover from the platforms, and then we made them smooth. And for our final scenario, we've removed the platforms entirely. Okay, so just going through some of the animations of our nearshore runs now. I've shown the reef platforms in white here. And so right away with the landslide case now, we can see the waves starting to interact quite a lot with the shelf and the reef platforms here. There's some very minor boundary artifacts here. And there's a heavy degree of scattering and reflection and refraction and shoaling as they propagate across this part of the shelf here. And so compare that with the earthquake case now. We had to shrink the domain here, but this is showing a kind of a close-up regional perspective of how the waves propagate across the shelf. And so there is a bit of a difference in the way that they propagate. The wavelength for the earthquake tsunami is much, much longer. And so there's much less scattering of wave energy. And you can also see some of the big platforms here. You'll see it as this wave comes in here. The big platforms are actually focusing tsunami wave energy. And the platforms will act a little bit like lenses where the wave will refract inwards and positively interfere in order to create larger tsunami amplitudes here. And so now just looking at the maximum offshore wave amplitudes here, this is essentially just giving you a snapshot of how big the tsunami is after it passes over the Great Barrier Reef. And so looking at the landslide case first, along the x-axis, we have a decimal degrees latitude. So it's essentially running parallel to the shore. To the left is the northern part of the shoreline where Kansas, and as you go to the right, you go further south. So hopefully that's clear. And so looking at the first case now with coral cover for the landslide case, the Noggin block case, tsunami wave amplitudes are fairly sizable here. They get up to about 30 centimeters or so just offshore. And when you remove coral cover from the Great Barrier Reef platforms, wave amplitudes go up quite a bit. And so according to these model results, wave amplitudes would double in some places if there's no coral cover on the platforms. And then finally, when you remove the platforms entirely, again, you see a very large jump in offshore wave amplitude. And so it's very clear that the platforms are incredibly effective obstacles in this case. And so now we're going to look at the hypothetical Solomon Islands earthquake case now. And I apologize for the difference in scale here. This is just so you can see the plot a little bit better. So when the coral platforms are rough, the tsunami amplitudes end up being about 12 to 15 centimeters max. And this is very, very reasonable for a tsunami of this kind with this kind of a source. And something a little bit different happens when we remove coral cover. So you do get a jump in offshore wave amplitude, and this is particularly behind really large reef platforms where they were initially covered with corals and they were initially causing a lot of attenuation of that wave energy. But once you remove the corals, the platforms actually get a lot better at focusing that tsunami wave energy. And so on a percentage-wise basis, though, it does seem like there is a buffering effect, but it doesn't appear to be as large as it is for the landslide case here. And then when we remove the platforms once again, we find that we do get jumps in wave amplitude, but not nearly as large percentage-wise as we would get for the landslide case. So why does this happen? Well, the degree of attenuation by bottom friction depends, and bottom drag depends on the particle velocity at bed as the wave passes over, and the bed particle velocity tends to be higher for waves of higher amplitudes. And so this is clearly the case for the landslide, which was simulated as a block falling in very shallow water. And in this part of the world, the tsunamis that are generated by earthquakes, they tend to not grow in amplitude too much by the time they reach the Australia. And so we further tested this idea that coral buffering would increase with tsunami amplitude, and we simulated a 9.0 earthquake case from the Solomon Islands, and we found that the reef buffered these waves a lot better, up to about 20 to 30% more. Okay, so just going to my conclusions, it appears that the Great Barrier Reef on both an ecosystem scale and a regional bathymetric scale significantly attenuates wave energy for landslide-generated tsunamis, and this potentially reduces the inundation risk for these cases, and this is good for us because landslide-generated tsunamis are very difficult to predict and forecast for. And on the other hand, for the earthquake-generated tsunami, it was much less sensitive to attenuation. Still, there was a buffering effect there, but it's still less sensitive to attenuation by bottom friction in comparison because of its relatively low amplitude offshore. And so in answer to my original question, does the Great Barrier Reef protect against tsunamis? Well, we would have to do a more detailed inundation study in order to know for sure. But it doesn't look like it affects all tsunamis equally. It probably does depend on the characteristics of the tsunami that you're dealing with. And it doesn't, the buffering effect isn't universal along the entire shoreline. It seems to be quite pronounced where you have the larger reef platforms that are covered with lots and lots of coral. And so I thought I'd close off by sharing some of my key lessons that I learned about numerical modeling in these types of environments. And it's just a couple more slides now. And this is where I think numerical modeling is also headed as a discipline. And so the first key lesson is that different model formulations, different discretizations, and different resolutions can completely alter one's interpretation of process. And I'll illustrate this with an analogy. And so if you come across a low resolution image that's highly pixelated, you might have some trouble identifying the object in the photograph. And the remedy for that, of course, is increasing the image resolution to capture more of the details. And the same principle applies for numerical models when you want to resolve physical processes. And this played a really important role in the first study that I mentioned on Contourite drift building. An earlier iteration of our model didn't simulate deep eddy circulation nearly as well as our current iteration of the model that we used. And so if we had used a prior version of the model, we actually may not have been able to provide a mechanism for what we were seeing, which is really critical when you're using numerical simulations. And so generally speaking, the higher the resolution and the more appropriate your discretization, the more you're going to be able to resolve and potentially explain. And I also mentioned for the first study that separate techniques all converged on a common mechanism for our observations. But I also want to emphasize that some mismatch between data and models is inevitable. And there are two main reasons for this. The first is that data often paints an incomplete picture and it's sometimes misinterpreted. And so the mismatch can be the fault of the data. And the second reason is that numerical models are imperfect representations of reality, and they are also misinterpreted at times. And so the mismatch can be the fault of the model as well. And these are two n-member scenarios, and the reality is probably somewhere in between. And the fact that there are data model mismatches it's not reassuring if you want to produce accurate predictions with a model. But for me, it was actually quite instructive because these data model mismatch can really help us to learn something new about process, and they can highlight areas where our interpretations of the record or our understanding of process could be improved or is currently incomplete. And finally, last key slide here, I'll briefly touch on where I think numerical modeling as a discipline is headed. And so firstly, going over some of the current shortcomings with these types of numerical models. The ocean model that we used in the first study required several months and hundreds of cores to run for one global iteration. And so these CFD models tend to be very computationally expensive to run. And this makes it very difficult to test hypotheses and to find the optimal configuration of parameters and to explore processes with traditional sensitivity analysis. And this also makes it difficult to use these kinds of models for forecasting in some cases. And so these models are also very complex, and this can make them quite difficult to interpret as a result. And so here are some of the potential solutions that I've seen popping up that have been used in tandem with these numerical models. And so we saw Professor Ryan Lowe give a great talk on his work that he did during his sabbatical, I believe, on smooth particle hydrodynamics. And these are very well suited towards problems in computational fluid dynamics. And so they're new ways of discretizing the space that you're trying to simulate, new methods that are popping up now and then. Optimization methods, which I'm sure a lot of you are familiar with, can automate the process of finding the optimal configuration of parameters for a numerical model in a way that best suits a given set of observations. And in particular, adjoint methods appear to be very promising in their ability to be used with computationally expensive models because they can very efficiently test the parameter space with a relatively small amount of model runs. And every single one of the models that I used is deterministic, meaning that there's only one possible outcome for each model run if you have a given set of parameters or forcings or boundary conditions. And probabilistic methods can help account for some of this uncertainty in the data and models and can help provide some insight about the likelihood of a given outcome occurring, given the likelihood of a certain parameter taking on a particular range, or the likelihood of a set of forcing or boundary conditions being used initially. So these are all popping up more and more in tandem with numerical models as well. And then finally, in some of the more fundamental computational fluid dynamics literature, where people are attempting to do things like train neural networks in order to mimic the behavior of numerical models. And the general approach, I believe, with this is that you run a bunch of model iterations at a time or ahead of time, and then you train the neural network on the parameters, on the forcings and the boundary conditions and the outputs. And the neural network can then give you a prediction much more efficiently. And this allows the technique to kind of capitalize on the known physics while coming up with a prediction very quickly that is consistent with previous observations. So this means that it could be quite applicable in a forecasting context. And so these surrogates can either replace the entire model or a series of models, or they can replace a process that's operating in the model, for example, such as simulating turbulence or simulating boundary layer dynamics. And so for the future of numerical modeling and machine learning, I think those two are actually one and the same. I don't have a general conclusion for this talk other than the fact that we should be doing as much interdisciplinary work as possible. And so I'll just leave you with these podcast recommendations. These are some of my favorite stories about the deep sea. Thank you very much for listening. I really appreciate it. It's been a pleasure talking to you guys today.
Thanks a lot, Mandi. That was a really impressive, kind of well-presented